nice down there. They're not social distancing. Yeah, it's not law. Each state is doing it. So that states are compliant. That's why we continue to have updates.
Okay, good morning. Any final questions? How are we doing today? Doing great. What would happen if we nuked the moon? So Luke, there's a
oh my God, this took me back home.
Seven Eves is a science fiction novel about exactly that topic. If you're
Austin is almost like basically the only city.
Yeah, Austin is the little teeny.
Okay, I muted you all. Sorry. So Luke asked, Luke asked, what would happen if we nuked the moon? If you're meaning literally, do we use all of the nuclear bombs that we have and place them on the moon and ignite them all at once? Nothing happens. We bounce some dust, make a big flash that we can all see, but the moon don't care. I mean, nuclear weapons are really big for humans, but they're not big for planets. Planets don't care. But anyway, go to the science fiction novel Seven Eves if you want to see what happens if the moon really blew up. Have I watched the Dune trailer? Yeah, it's awesome. Anyway, that's it. Let's talk about astrophysics today. So today is all about the sun. And I'll tell you why we want to study the sun. We'll go into detail. Today's lecture, there's very little math in the lecture, but lots of detail that you're going to have to know for the second exam. So let's get started. Here's a documentary picture of the sun. Anyway, I love this drawing. And just to refresh your memory, we have finished with the first part of the course, which is the introductory, kind of the physics-y part of the course, where we talk about kind of gravity, electromagnetism, light, the night sky, and things like that. Today, we start on the stars part of that. And the very first lecture on the stars part is the sun, because the closest star we have is the sun. And so we want to study the sun as much as possible if we want to understand stars. And then the latter part of the course is about galaxies. And we have an exam on October 1st. So that's a week and a half from now. So here's what we're going to be talking about today. Studying the sun, solar interior, photosphere and chromosphere, the solar magnetism, and the corona and solar wind. So basically, we're not doing a lot of theory. We're doing a little bit of theory, but mostly we're describing the sun. And so the first Dune is anticlimactic, but remember, Dune was a series of books. So anyway, here's a photo from NASA that I was able to obtain. A leaked photo of NASA taking the sun down for maintenance. I thought that was cute. So let's talk about study the sun. Why do you want to study the sun? Well, as I mentioned before, we want to study the sun so we can understand stars. And if we understand stars, then we understand the cosmos. And this has been the primary goal of astronomers for the last couple hundred years. Before that, astronomy was much more descriptive than trying to understand. But that's only the first reason we want to understand the sun. The second reason is we want to deal with solar superstorms, and we want to prevent the collapse of civilization. We'll talk a little bit more about this later in the lecture. If a solar superstorm happened today, a civilization would collapse. Billions of people would die, and we'd be back to stones and sticks. The third reason we want to understand the sun is to really understand the solar cycles, and again, to prevent collapse of civilization. Because if the solar cycles change, which they have in historical times, the planet isn't bothered, but our civilization will be crispy crittered. We'll talk more about those last two things later, but as you can tell, it's important to understand the sun. It's our closest star. So I've got a bit of analogy. It's a little strained, but I want you to think about this. Let's say that you're an alien civilization and you want to understand human civilization, not just the planet, not just humans, but our civilization. But the problem is, not only do you have poor resolution, but you can only observe us at a single point in time. So you get a snapshot of the Earth. And so follow me through with this analogy. So if you want to understand civilization, you should first understand the components of that civilization, and the obvious component of that is humans. So you can observe them with electromagnetic radiation, and since you can only observe humans at a snapshot, you have to, and you see little humans and you see big humans, you can infer with models that little humans turn into big humans, okay? It's a model. You can't directly observe the birth and the lifetime of a human because you're only observing the planet at a single point in time. So you create this model for a human lifetime. And then you can see all different types of animals. You can see, you know, lizards and deer and bacteria. Well, maybe not bacteria, but spiders and whatnot. And you can develop a model of evolution. You can say, well, all of these life forms are related, and you would develop models for how they're related. Actually, it's not that dissimilar from archaeology and anthropology. So, but again, you can't observe a human lifetime. You can't observe the evolution, but you can develop models based on a single observation. Well, then you have to understand how these humans interact, the civilization itself. And so you observe collective behavior, and again, you develop models for the way humans interact. So we have models on top of models, and that's really all we can do. But you can certainly, you've got so much data, you can test those models and see if they fit the observations or not. But at the end of the day, with all these models and lots of observations, even if it's a single point in time, you probably wouldn't be too far from the truth, okay? So why am I going through this very long analogy? We have the same problem looking at a star. We can only see a star at a certain point in time. We can observe it. We can observe its brightness, its color, its temperature, and its location. And we can do that actually just by looking at it. And as we mentioned last time, with those spectral lines, we know what they're made of. We can know how fast they're moving towards or away from them. We can know if it has exoplanets. We'll talk about that in a bit. But if the exoplanets pass in front of the star, we can see the star dimming. We can tell its magnetic field by the way it moves the spectral lines. We can tell if the star is spinning by the way that the spectral lines move as the star spins. We can tell the surface gravity, that's kind of a detail. We can tell if it's a binary system because we can see the star warp back and forth. So even though we're observing that star at a single point in time, we can tell a whole bunch. But really, we would like to know a bunch more. Now, if we have the distance, we know not just its brightness, but its luminosity. I can tell you what its size is. I can tell you what its mass is. I can tell you what its density is. But what we really want to know is, what are the different types of stars? Are there categories of stars? And why are they different? What separates them? How old are the stars? What is their past history? And what is their future? And what defines habitable zones? We'll be talking about that in the next to last lecture of this class. To do that, because we can't observe at different times, but we can observe all stars now, again, we have to develop models, and that's what we've done. This lecture is mostly about observations. We'll be talking about a few models. In future lectures, we're going to go into those models in great depth. And those models are actually really, really good, okay? Lewis says, do people in the ISS feel solar flares more intensely than we do? The answer is yes and no. The answer is yes, they do have a higher radiation load than we do, but they are protected from the worst part of solar flares by the Earth's magnetic field. If they were outside low Earth orbit, they could be crispy crittered in seconds. And so every time we left low Earth orbit, which we've only done for 12 people ever in the history of our civilization, they were at risk. And if there had been a solar flare during any of those Apollo missions, it would have been a bad day. Can astronomers predict when a solar flare would occur? Yes and no. It's kind of like we know the conditions are right for solar flares, but we can't predict, you know, we can't give you 2 days warning a solar flare can hit. We can give you about 30 minutes warning. We'll talk about that towards the end of this lecture. So to develop these models, what we want to do is study the closest star we have as closely as possible. And it's a pretty dramatic. Notice the size of the Earth. The Earth is 1/100th the size of the Sun. So remember, from the Earth to Jupiter is a scale of 10 to 1, and from Jupiter to the Sun is a scale of 10 to 1. So the Sun is very active and lots of stuff happen, lots of extremely violent stuff, of which the Earth is just a minor little drop in the bucket. So here's the surface of the Sun, and there's the Earth 2 scale. So, you know, everything we know has happened in that pale blue dot right there. And there's the Sun. The Sun is big. And as stars go, our Sun is not particularly big. Our Sun is one of the smaller stars out there. You can observe the Sun in many different frequencies. And when you observe it at different frequencies, different electromagnetic radiation bands, you get different views of it. And we'll talk about that later in this course. So there's what the Sun looks like to the visible eye. Here's what the Sun looks like to ultraviolet eyes. And now we're getting into the X-rays. And there's more X-ray shots there. Okay. And now we're getting into the very high energy X-rays. So different layers of the Sun are at different temperatures, and we'll be talking about that in a bit. It's crazy. I watched a TV show that had a solar flare in it. A spot on the Sun heated up and caused all electronics to malfunction. Gracie, it's much, 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 much worse than that. If that's all it caused, it would be an irritation and would cause trillions of dollars worth of damage. But a massive solar flare, such as what happened in 1859, would take down the entire power grid all over the world. And because it would fry every transformer that was connected to that power grid, it would take months to years to recover. So can civilization survive with 6 months with no electrical power? Good question. So any minute, humanity could be wiped out by a solar flare with barely any warning. Alex, that's exactly correct. Okay, here's a time picture of the Sun, and look at the time down in the lower left. So now the Sun rotates. The Sun rotates once every 30 days. So the face of the Sun will rotate across, you know, in 2 weeks. Now this picture happens to be in X-rays, but you know, there's other bands, and you can just see all the activity that's happening all the time on the Sun. So in this lecture, we'll be talking about the Sun. So Cole says, how come no one is prepping for that? Yeah, well, you know, that's an interesting question. How come nobody is prepping for the supervolcano that might happen in Yellowstone? How come nobody is prepping for the massive earthquake that could happen in Seattle? These are massive things that will affect civilization, but don't happen that often. They happen over hundreds of years. The problem with the solar superstorm, okay, I'll talk about this later, but let me tell you briefly how to prevent the entire civilization from collapsing. And that's if we'll have about 30 minutes warning, and in those 30 minutes, we tell the worldwide power grid to shut down physically, disconnect all their transformers and relays from the power grid, and we would be protected. And then we'd just power it back up. The problem is, you shut down the worldwide power grid. First of all, who is going to believe you? People are going to believe you when you have credibility. Does the United States have any credibility right now? Okay. And not only that, but shutting down the power grid, if you're wrong, you've caused hundreds of billions of dollars worth of damage just in that prophylactic shutting down the grid. So yeah, there's a technical solution to this. Is there a political solution? The political solution has to come with trust, of which we have none right now. Anyway, let's go on. And so here is a picture of the sun over years. And what we've noticed is that the sun gets really active and then it gets less active, and really active and less active. Okay, it's called the sunspot cycle, but it's really the total activity of the sun. And this graphic there shows the activity of the sun as it increases and decreases. Now that towards the end of this video, you're going to see it increasing again. Okay. And when it's at its maximum, it's called the solar maximum. What if the warning came from NASA? Surely they're credible. Yeah, hold that thought. The problem is that we have only one satellite, to my knowledge, that could possibly detect the solar storm, because it's not the light which we can detect that gets you, it's the particles, and the particles have to be detected in place. We call it in situ. And there's a satellite called ACE, which is out there detecting it. Also, GORSAT, I think, has a sensor. And those are only a couple of million miles from Earth, and that would only give us about 30 minutes to an hour warning. And so you can't see them, you have to detect them. Now, I know to listen whenever somebody tells me an incoming solar storm. Yes, now the solar superstorm will not hurt you, and it probably won't fry your cell phone. What it will fry is the cell phone network. If you're an astronaut, you're dead. Sorry. But we will not die. No human on the surface of the Earth will die instantly because of the storm. Only long electrical wires will build up a charge and fry whatever at the other end of them. So here's a nice cartoon. How worried should you be if you see local reporters interviewing scientists about a breaking news story by field? Well, archaeologists, you don't need to be too worried. Botanist may be really worried. I know virologist is up there. You need to be really worried. And the highest object is astronomer who studies the sun. Anyway. So let's talk about the sun itself, the solar interior. Again, we're going to go over this very lightly. We're going to go into great detail when we study stars in general. So here are the layers of the sun you're going to be responsible for. We've got the core of the sun, just like the Earth has a core. Then we have two layers called a radiation zone and a convection zone. Those layers are named for the way energy is transported through those layers. The radiation zone is energy is transported through that layer by radiation, okay? The convection zone, and we're going to talk more about convection, is where energy is transported by the bulk motion of the liquid, I'm sorry, not the liquid, the plasma that makes up the convection zone. This is identical to what happens in the Earth's core, by the way, because the mantle is convective, and those convective cells in the Earth's mantle is why we have plate tectonics, why North America and South America are moving away from Africa and Europe. Okay, and we'll talk more about convection in a bit. You are responsible for these layers: core, radiation zone, convection zone. The next zone, which is the most important zone for us, is called the photosphere. Photo meaning light, and that is the surface of the sun that we see. So when we look at the sun, for the few seconds before we lose our vision, because our eyeballs have just been fried, we are looking at the photosphere. Above the photosphere is something called the chromosphere. The chromosphere is kind of boring. We don't talk a lot about the chromosphere. We don't talk at all about the transition zone. Don't worry about that. But then the highest layer, which would be equivalent to the Earth's upper atmosphere, is called the corona. The corona is really interesting, and mostly you cannot see the corona. The only time you can see a corona with the naked eye is during a total solar eclipse, which I hope most of you saw during the 2017 total eclipse. Now, if you stayed in Raleigh, you didn't see a total eclipse. You saw a partial eclipse, and you did not see the corona. But if you actually traveled to the west, or traveled to Oregon like I did, or someplace where you could see the total eclipse, you know exactly what I'm talking about. Okay. So the models that we have of the sun, these models we began to develop these models in the late 19th century, early 20th century. We just use basic thermodynamics. The deeper you get, the higher the pressure is. And for those of you that are divers, you know this instinctively, that the deeper you get in the ocean, the more pressure you feel. And that's going to be true in any object. If you drill down into the earth, it's going to be higher and higher pressure. If you go down in the sun, it's higher and higher pressure. And what happens when you increase the pressure? You increase the temperature. So diesel engines, gasoline engines, the piston comes up, takes the fuel air mixture and compresses it. And as it compresses it, it heats it up. And in a diesel engine, it heats it up to the point where the fuel air mixture ignites. That's how a diesel engine works. It's by this compression that heats things up. Same thing's happening in the sun. The sun has higher and higher pressure as you get closer to that center. And as it has higher pressure, it has higher temperature. Okay. Didn't the path cross South Carolina for the eclipse? Yes, it did. Does the sun have a specific surface, or does it just get less dense as it goes out? So the definition of the sun's surface is what we see when we look at it with our eyes. Okay. And that's the photosphere. Now, if you looked at it with different eyes, such as X-ray eyes, you would see a different level. But by definition, by our definition, the photosphere light is the surface that you see. Just like the gas giants, Jupiter and Saturn, they don't really have a surface per se because it's all gas, but we talk about Jupiter's surface because we talk about the layer that we see with our eyes, okay? Where the gas is so dense that light doesn't go any farther. Same thing with the sun, except on the sun, it's not gas, it's plasma. Let's see. And yeah, I believe you could see it from Columbia, South Carolina. Okay. So actually, I just, let me do a quick poll. Let's see. Let's do a poll. And I just for my own curiosity. Okay, so 8 of you at least saw, or 9 of you saw the total eclipse, and it's an amazing experience. I just remember the shadows being super trippy, absolutely. How would the solar storms effect compare to an EMP? So Alex, the solar storms effect is very similar to an EMP, but the difference is an EMP only affects a certain area, you know, a circle of 100 miles or so. Whereas this would be over the entire surface of the earth. Okay. Anyway, that's just interesting. So let's go back to here. So how does the sun shine? The sun shines because it doesn't shine through chemical reactions that we have on the surface of the earth, that we use day to day. I mean, if we want to make a power plant, we burn fuel, it heats stuff up, it heats a boiler, and it spins a turbine. We're using the chemical power of rapid oxidation, taking carbon atoms and combining them with oxygen atoms, and we combine carbon with oxygen in a certain way. They move really fast, and the outcome is heat, and we use that heat to move generators, generate power, do various things. Sun doesn't operate that way. And if it did operate that way, it wouldn't last very long. And in fact, this was a big crisis in all of science at the end of the 19th century, because the estimates for the age of the sun based on rapid oxidation, based on chemical reactions, was just a few million years. But we knew from geologic evidence that the earth was hundreds of millions, if not billions of years old, and that just didn't square up. And the problem was they didn't know about nuclear energy back then, and now we do. Nuclear energy is, instead of atoms combining, we have the neutrons and the protons combining. And the difference in energy is astounding. We'll go over this in great detail when we talk about the universe and the Big Bang. Difference in energy is a factor of a million to a billion to one. In other words, I might be able to generate 1 eV, which is a unit of energy, when I do a chemical oxidation. I can generate tens of millions of eV for that same operation between two atoms when they combine or they fuse. The sun, the primary energy source of the sun is nuclear fusion. Fusion meaning combining of the elements. So in particular, we have four hydrogen atoms combining to form 4 helium atoms and then producing energy. There are other sources of energy, but those are the primary ones. And we'll talk about these a little bit more detail in the next lecture and in much greater detail when we talk about the beginnings of the universe. So this is a chart. It's hard to understand. I'll be showing this chart periodically through this course, but I want you to keep this chart in mind. And what this is if you sail down this curve, you can generate energy. So when you go from hydrogen to helium, which is down there, going from hydrogen to helium, you generate energy through mc squared, actually. So 2 hydrogen atoms weigh more than a single helium atom, okay? And that energy, the difference in the mass between those is sent out in terms of, is the energy generated by that fusion. Now, when you when you turn on the light bulbs now, any place in North Carolina, part of the energy from that light bulb comes not from nuclear fusion, but what we call nuclear fission, where you take an atom and instead of combining atoms, you split those atoms apart. And what you have here is, on the same chart, we have uranium. And if you split uranium apart, then you generate energy. Again, going down this curve, you generate energy. So in other words, the atoms that you split apart weigh less than the uranium that you started with, okay? So again, you want to go down, and when you're on this side of the curve, to go down, you split apart. When you're on this side of the curve, to go down, you fuse, okay? So this is nuclear fusion, nuclear fission. And in both cases, you're generating a mind-blowing amount of energy, but just in different ways, okay? So nuclear fission is not a factor in stars and astronomy. It's only a factor in nuclear power plants. Nuclear fusion is the whole ballgame. And there have been lots of nuclear fusion experiments on the Earth. If we ever have a practical nuclear fusion reactor, since basically the fuel for a nuclear fusion reactor is water, we would have a limitless source of energy forever and ever. And that's why we're spending hundreds of billions of dollars in research trying to develop a practical nuclear fusion reactor. And we've been doing it for 50 years, and we'll do it for another 50 years until we're successful. That, by the way, will solve the climate crisis, because this doesn't produce global warming. It doesn't produce CO2. So, sun by the numbers. Here's what the sun is made of. It's mostly hydrogen and helium, and then a smattering of other stuff. Now, in your day-to-day reactions, when you burn stuff, you might change the characteristics of the molecules that surround you. So when I burn stuff, I turn carbon into carbon and oxygen. I turn it into CO2. I can split apart water into hydrogen and oxygen. When I eat stuff, there's a chemical reaction. So I'm constantly moving apart atoms and making different molecules, but the elements themselves are unchanged, okay? That's not true in stars. In stars, elements are created. And so in our star, hydrogen and helium are the primary constituents. And in fact, hydrogen is being changed into helium, transmutation of the elements, but then we have a smattering of these other elements. Some of these elements were inherited from previous generations of stars, and some of these elements were actually created in our stars. but these are nuclear furnaces that create different elements. Okay. And just by the numbers, the radius of the sun is about 700,000 kilometers, as opposed to 6,500 kilometers for the Earth. So again, the sun's radius is about 100 times the Earth's radius. And the mass, you would expect the mass would be the volume is the radius cubed. So you would expect the mass to be about 100 times 100 times 100, about 1,000,000 times greater. And that's about right. The mass is about 1,000,000 times greater. Density of the sun overall is less because the sun is made of plasma, not of matter. The Earth rotates in one day. The sun rotates. It's huge. Remember how big that is. It takes an entire month for it to rotate. How stable is the gas of the sun? If we threw something in there, would it cause something to happen? You're probably talking about the movie Sunshine. The answer is no. By stable, we'll talk about stability. So our sun, compared to other stars, is extremely stable. And that's kind of a selection effect, because if our sun was like other stars, we wouldn't be here, because we could not have evolved, because our planet would have been periodically sterilized. So we are here by the fact that our sun is incredibly stable. Even though it's incredibly stable, it still varies, and it varies for various reasons. We don't understand all those reasons, but certainly one of those reasons is magnetic, and we'll get into that in a bit. Okay. The surface of the sun is 5,800 degrees. And if you remember the discussion of black body thermal continuous radiation last time, when we had the black body spectrum that peaked at around 5,800 degrees, the red, green, and the blue were all about the same. It peaked in the green, but we had so much red and blue that to the eye it looked white. That's not accidental, okay? 5,800 degrees is what the sun produces, and that's what we perceive as white, okay? Our eye's 3 color sensors are finely tuned specifically to our sun, okay? Whereas the Earth's temperature average is about 254 degrees Kelvin, which is actually below freezing. Surface of the sun that we see is called the photosphere, and of course, the surface of the Earth is just the surface of the Earth. Okay, so that's the solar interior. Now we're going to talk about the photosphere and chromosphere. The photosphere and the chromosphere are the two outermost layers of the sun. The photosphere is what we see. The chromosphere sits on top of it, and it's translucent. You can see through it, because if you couldn't see through it, then it would be the photosphere. Okay, and it sits directly above the convective zone, and we'll talk more about the convective zone later. So what do we see when we look at the photosphere? What we see is this kind of a boiling effect. It's difficult to see here. You're going to see it better in another video. That boiling effect is exactly the same. It's exactly the same as if you take a pot of water, you put it on a stove, and you watch it boil. When you watch it boil, it will tumble, okay? And that tumbling is called convection. And what happens is the hot water at the bottom of the pan rises up to the top of the pan, because heat rises, hot things rise. And as that hot water rises, it displaces the cold water on the top, and the cold water comes back down. And that cold water is then heated up, and that rises, and you develop this convective loop. And the top of that convective loop are the granulations that you see on the surface of the sun. And here is a picture that was just sent out just a couple of months ago. Look at the size of those granulations. And remember, each of those is larger than the Earth. And you can see the time here. The time scale is minutes. Okay, so let's talk a little bit about the convection that you see there. So here we have a hot plate and a cold plate, and the hot plate heats that up so the hot water rises, and as it rises, the cold water has to come over to take its place. But now that cold water is heated up and it rises and it creates this convective cell. And the size of the cell is going to be approximately the size of the convective zone. Okay. How is the camera lens not fried when taking pictures like these? So those images were actually taken by a ground-based telescope, and they have massive cooling. The Parker probe, which was a solar probe that just flew by the sun, the cooling was the major part of that. And I'm really not sure how they did that. Presumably with, my best guess is they had a mirror that was deeply cooled before the light hit and decreased the amount of light before it went into a lens system. But yeah, that's a big problem with solar telescopes. So here's the chromosphere. The chromosphere sits on top of the photosphere, and it's translucent. Who cares about the chromosphere? Sorry. Just know that it's above the photosphere. Here's the big kahuna. So we talked about the two major reasons, besides trying to understand the universe, that we study the sun, is trying to keep it from killing us. And the major thing that's going to kill us with our sun is solar magnetism, okay? So what kind of system can effectively cool something enough to combat the sun? Well, I mean, we do that every day when we go outside. You know, you put up sun shields. You sit under an umbrella, for example. And so, cooling a solar telescope on the surface of the Earth, we have the technology to do it. We do it every day. Doing that technology for a probe that's near the sun, I actually don't know how they do that. That's a good question. So the most visible appearance thing of the sun that's based on solar magnetism are called sunspots. And for those of you that have eclipse glasses left over from 2017 or have solar filters, with the naked eye, you can look up at the sun. With the naked eye, you can see sunspots if they're big enough. Okay, sunspots are like pimples on the surface. And here's the thing: the Earth would fit inside this sunspot. Okay, and so here is a sunspot. A sunspot grouping that moves across the surface of the sun. And notice here, November 7th, 10th, 12th, 14th, okay? The ancients could have seen and did see these sunspots, okay? And there is the approximate size of the Earth. So what causes these sunspots? What causes these sunspots is the sun's magnetic field, okay? So most of the surface features involve magnetic fields, not the granulation. The granulation is caused by convection, but all the other features such as the sunspots and the solar prominences and the solar flares, coronal mass ejections, and the things that are going to kill us are caused by interactions of the magnetic fields. Charged particles travel along the magnetic field lines. The sun is made not of gas, the normal gas that we're familiar with. It's made of what's known as plasma. Plasma is where the gas is so hot that the electrons are stripped from all the atoms. And so what you do have is naked atoms with no electrons and naked electrons flying around. And that fourth type of matter is called plasma. And because plasma is highly charged, when you put a magnetic field in a highly charged gas, things happen, okay? And so those sunspots are actually the origins of magnetic fields on the surface of the sun. So typically sunspots will come in pairs, not always, but they often do, where one part of it will be the north pole of a magnetic field and the other is a south pole of a magnetic field. So it's like the magnetic field erupting from the surface. And in fact, you can see these tracers, these solar prominences, that actually trace that magnetic field. And again, this is several times the size of the Earth. So the sun rotates, and I said it rotates in about a month, but it's not solid, and it doesn't all rotate at the same speed. So in fact, the sun rotates faster at the equator than it does higher up. And that faster rotation causes a dramatic problem with the magnetic field of the sun. We don't have this problem on the Earth because the Earth is solid. The Earth rotates at the same speed. But anytime you have this differential rotation, what's going to happen is you're going to get this shear of the magnetic field, and that shear is going to cause problems. So here's the sun's magnetic field, just like the Earth has a magnetic field that's aligned with the spin axis. But because of that differential rotation, it's going to distort that magnetic field. And here's the way it distorts. And as the magnetic field gets more and more distorted, it starts breaking up and getting really nasty. And that breaking up and getting really nasty is what causes those sunspots and those solar prominences and the solar storms. And here's a simulation. And here the green represents the north magnetic pole, the purple represents the south magnetic pole of the simulation. The simulation is going to be running from 1997 further. And what it's simulating, actually, this might be observations, but so in 1997, the sun was at a minimum solar activity, and then it comes up to a solar maximum and then a minimum year. So watch the simulation. As we go from year to year, green at the top, purple at the bottom. Green at the top, purple at the bottom. And notice the magnetic field gets so chaotic that at the end of the video, we have green at the bottom and purple at the top. In other words, the magnetic field of the sun has flipped. And that flip happens over 11 years, okay? So the sunspot has an 11-year cycle where that magnetic field gets wrapped up on itself, gets chaotic, it flips, and then it just says, I give up, and it reforms a new magnetic field. And it has an 11-year cycle. It's approximately 11 years. It varies a little bit. Sometimes it's 10 years, sometimes it's 12 years, okay? And here is a chart of the number of sunspots. And the number of sunspots correlates with this chaotic motion of the magnetic fields. And when it's at its most chaotic, we have its most sunspots. And when we have the most sunspots, the sun is the most active in terms of those prominences, those arcs, and those solar flares that come towards the Earth and make our life miserable, okay? So here's the chart for going from 1950 to 2010. And notice we've got this 11-year cycle, but there's variations in these peaks, okay? So there's variations every 11 years, but there's also variations from cycle to cycle. Also note that every cycle has a different orientation. So the cycle is 11 years, but the north magnetic field is up here, down here, up here. And so some people talk about a 22-year cycle where the magnetic field flips, everyone. But normally day to day, and certainly you will be tested that it's an 11-year cycle. Okay, and so here, the solar sunspots tend to start at high latitudes and then migrate to low latitudes. And that's just because as the magnetic fields wrap up, they tend to get more chaotic at high latitudes first, and then that chaos migrates down. And here's a longer chart from 1880 to, well, today. This should be filled in, but look here. There's just huge variations, okay? And if you think that's bad, let's go back even farther to 1600. And there's something called a Maunder, I'm sorry, I have trouble with words. Maunder minimum. So between 1600 and 1700, there were no observed sunspots. And off this chart back, in 1400s, we did observe sunspots. And then there were no sunspots observed in this region. And then sunspots were observed later on. So during this time of the minimum, no sunspots were observed. The sun was quiescent, and Europe went into what's known as the Little Ice Age. And so we're not completely sure of the mechanism, but clearly there's a strong linkage between solar activity and the Earth's climate, okay? So in particular, we're warming up the planet right now by injecting CO2 in the atmosphere. I think there's no doubt about that other than our current administration. Every other rational person in the world realizes that. What people don't appreciate is that the solar cycles are actually somewhat quiescent right now. If we hit a peak like we hit in 1950, that would double or triple the problem. It would make it would be heating on top of heating. It would make the global warming that much worse. And so we're getting a slight breather from the sun, but there's no guarantees that that breather is going to last. Okay. So this is the thing I was saying, truly understanding what causes these variations, which we don't fully understand now. These variations in the solar cycle could be critical to our survival. Okay. So now let's talk about the corona and the solar wind, which are caused by these magnetic fields. So the corona, so we've got the photosphere, we've got the chromosphere, which sits on top of the chromosphere, we got the transition zone, which you're not responsible for. Then we have the corona. The weird thing is the photosphere is at 5,800 degrees by definition. That's what we see, that's the surface. Typically, things get hotter as you get deeper. So for example, the Earth, the surface of the Earth is 254 degrees. The center of the Earth is about 6,000 degrees, which is exactly what you would expect. The more pressure something is under, the hotter it is. And on the sun, the surface of the sun is 5,800 degrees. The core is about 10 million degrees. And we'll get more into that when we talk about the sun, stars, which is exactly what you'd expect. So you would expect the corona to be cooler, just like the Earth's upper atmosphere is a lot cooler than it is at the surface of the Earth. When you're flying in the stratosphere and you're Boeing 737, it's going to be 40 below zero out there, and you definitely do not want to open the door. And you really don't want to open the door in a 737. Okay. The corona is at millions of degrees. The corona is much, much hotter than the photosphere. Why is that? So here is a chart of the temperature. Temperature of the photosphere. The chromosphere is here. The chromosphere is a little hotter than the photosphere, not a lot. And then all of a sudden we see this huge jump to millions of degrees to the corona. And here are pictures of the corona from various satellites, okay? And it extends very far away. It's like the sun's atmosphere, but it's not quite like the Earth's atmosphere because it's so hot and it's so extensive, okay? Here is a picture of the corona. I took this picture in 2017 during the 2017 total eclipse. I was in Oregon when I took that. The only time you can see the corona is during total solar eclipse, where you're able to block the sun from the Earth, from the sun's photosphere by the moon. Now, someone else took a better picture. Okay, so no matter what you do, somebody else did it better. Coming from the corona is what's known as the solar wind. So we have these solar, all the solar activity at the surface, which heats up the corona, and then it's so hot and it's so energetic, it spews off from the sun in what's called a solar wind. The solar wind consists of very rapid, very hot charged particles that spew from the surface of the sun. It does it, yours is easily the best picture I've seen. Well, thank you very much, Sam. I took it with my Nikon camera. I took about 20 pictures. I set up a timer to take 20 pictures in about a second at different exposures, took those pictures into Photoshop, aligned them, and then did some magic. And, 2 days later, I came up with that image. The reason why is that the corona varies so dramatically in intensity that you have to take a whole series of exposures to get that. So taking good eclipse photos is a real art. So the solar wind is a constant flow of particles, velocity here. Now remember, 30 to 800 kilometers. This is not kilometers an hour. This is kilometers a second, okay? So remember, when you go up around the Earth, you're going a few I forget, was it 7 or 8 kilometers per second when you're in orbit? And that translates to 17,000 miles an hour. So 300 to 800 kilometers per second is really, really, really fast. Okay. And that solar wind comes towards the Earth. And here is part of that solar wind. You can see this eruption here from this solar prominence. Now, when there's a really large eruption, we call that a coronal mass ejection. Okay. So CMEs, solar prominences, solar wind, they're all part of the same phenomena, but just at different intensities. And the most intense are called coronal mass ejections, or CMEs. There's a CME. So that solar wind and the solar flares, they spew these charged particles, but they don't hit the surface of the Earth typically. What they do is they hit the Earth's magnetic field. We have a relatively strong magnetic field as planets go. And because these particles are charged, they hit the magnetic field, and instead of continuing on to the surface of the Earth, they have to follow the field lines, and they sit there and they spin. And they spin and they come down the magnetic field lines, and the magnetic field lines of the Earth are concentrated at the north and south poles. And when those charged particles hit the Earth's atmosphere, they make the atmosphere glow. And this is called the aurora borealis. How many of you have seen the aurora borealis? Say yes in the chat if you've actually seen it. I've seen it a couple of times when I was canoeing up in Minnesota. But you can see it a lot if you're in Alaska, for example. It's quite the sight to see. It's almost it's a transcendental experience because the entire sky is moving and it's all silent. It just feels really weird. Here's a picture of the aurora borealis from space, and you can see it literally circles the Earth. How close can a human get to the sun without getting burnt to death like a barbecue? Depends on how big your sunshade is. So if you are at the orbit of the Earth unprotected, you would be crispy crittered fairly quickly. And so there's really no good answer to that. It's really depends on your protection. The reason we're not crispy crittered is because the Earth's magnetic field and the Earth's atmosphere protects us from all the nasty ultraviolet and X-rays and gamma rays that come from the sun. And so these aurora borealises are not unique to the Earth. Here's aurora borealis on song to make up for the fact that they made a mistake in the earlier song. I'm going to talk a little bit about the Great Solar Storm of 1859, when the Greenwich Magnetic Observatory detected disturbance in the magnetic field. And we now know that these coronal mass ejections were moving very fast. Normally they move at 800 kilometers a second. This is moving at close to 2,380 kilometers a second. This is the fastest coronal mass ejection that has ever been observed in history. And it hit the Earth so hard and so fast that instead of the auroras being centered at the north and south magnetic poles, you could see the auroras in Venezuela and down as far as Florida in the United States. Okay, the sky was on fire. Telegraph offices burst into flame. They induced electric charge fields in these long telegraph wires and fried people that were on the other side. Miners ate breakfast at 1 a.m. because it looked like it was daylight. The telegraphs were unusable for several days. But here's the thing. The only thing electric in operation in 1859 were telegraphs, and they were fried. And then they recovered, of course, because it wasn't terribly high technology. But nothing else was affected because their civilization did not depend on electricity. Well, we're not so lucky. So here's a listing of storms that have happened since then. So 1859 is the mother of all superstorms. In 1972, it took down the power grid over the Northeast. Here we have various satellites that got fried by those magnetic fields. And in 2005, a solar superstorm really was a danger to even the ISS astronauts, although they're under the Earth's magnetic field. And they had to go into their safe room. Okay, there's an area in the ISS that's considered that has more shielding than other parts of it. Okay, so here's what would happen if a solar storm hit us. Anything outside the Earth's magnetic field would be crispy crittered. So your communication satellite that are at thousands of miles up, your GPS satellites, which are slightly above the Earth's magnetic field, they would be crispy crittered. Any astronauts that are above the Earth's magnetic field would be crispy crittered. So you would lose hundreds, if not thousands, of satellites. And then you would have minor disruption of your electronic devices. The major problem, and if you're in an airplane, you've got a problem because you're going to get a huge radiation dose. Down at the surface of the Earth, you're really fairly protected, but the Earth's electric grid is not. The longer the wire, the larger the electric field that's generated in that wire, and the more chance there are of frying the relays on each side. Those relays get fried. Some of those transformers cost millions of dollars and take 6 months to build new ones. And so that's the major disruption. So the worst case scenario, we've got a power grid, we've got scattered electronics, no GPS. Most satellites are going to be fried. Cockpit electronics are going to be fried. So pilots that are in the air at the time are going to have a tough time figuring out how to land. And the problem is, so much of our modern technology, astronauts would be crispy crittered even if they had a safe room. If they're above low Earth orbit, yes. Now in the ISS, you're fairly protected, so they're going to get a high radiation dose, but they're not going to be crispy crittered. How long would it be until the start of the solar storm until it's safe to turn everything back on? So here's the thing: the storm only happens over a few hours, but those relays are fried. You have to make new relays. They're not just sitting on the shelf someplace. That's the problem. The problem is these major multi-million-dollar relays and transformers are not sitting in a warehouse. They have to be built, and you need power to build them. And the problem is we've seen this with the COVID virus, is that our technological society is deeply intertwined, and you disrupt it even a little bit, and you don't have any toilet paper, for example. But here we're talking about a massive disruption. We're talking about no power. So that's going to have a dramatic effect on transportation. It's going to have a dramatic effect on your finance system, on the oil and gas extraction system, on your emergency services, on everything else. Now, 10 years ago, the National Academy of Sciences predicted this would be a $2 trillion problem. Actually, it's probably literally astronomical. It probably is so large you can't even compute it. You would have to, you would have a new civilization after this event. So that's the worst case scenario. And it looks like I'm out of time. I don't have time for questions, so let's open it up for discussion. Feel free to turn your mic on. Thank you very much. I just thought this was a nice, optimistic lecture. I thought you'd enjoy it. Questions? Say if we found a cheap way to do it, could we send all our trash so it would just burn up? Yeah, people have actually talked about sending our trash directly into the sun, especially our nuclear waste. And certainly you could do it, but boy, the expense is breathtaking. Is there a way we can do our house disconnect our power to stay safe and keep power? Or is it the city's job? So probably your electronics in your house are safe, and probably the power lines from your main power distribution to your house are safe. What is at risk are the long distance power lines, like the power lines that go from the nuclear power plant down the street to us, the lines that go for hundreds of miles. Those are all going to be fried. So, people that have solar power grids on the surface of the house, they're going to do fine. They're going to do fine. In other words, their house is going to have power, but where are they going to buy their food? And who's going to take care of them? And where are they going to get the gasoline for their car? So it's not just you and your technology, it's civilization. How does the solar wind affect us on Earth? I read somewhere that it could damage GPS satellites. That's exactly what I was talking about, Lila. I'm sorry, I mispronounced your word, Laya. The GPS satellites, because they're in a relatively high orbit, are at risk, and they are somewhat hardened against radiation, much more so than low Earth orbit satellites. But a massive storm such as the one that happened in 1859 would fry even the GPS satellites. And so again, they do have a high radiation dose. They're designed for that, but they're not designed for a superstorm. Is there a guess of when the next solar flare is going to hit the Earth? We have absolutely no clue. It's like predicting when the next earthquake is going to hit Seattle. We know that Seattle earthquakes, which are beyond anything that has happened in historic times, happen on a scale of 1 every 1,000 years, but we don't know when in those 1,000 years it's going to go happen. The same thing with solar superstorms. We know that solar superstorms, we're guessing, happen over a time scale of 500 to 1,000 years. We're guessing, but we have no clue if it's going to happen tomorrow or in 500 years from now. Does the rotation of the sun cause any noticeable change in the temperature of the Earth? So short answer is no. Long answer is what happens on the sun does have a dramatic effect on the Earth's climate in ways that we don't fully understand. But certainly there's a strong linkage between solar activity and the Earth's climate, and we don't know why. Can you show us the theremin one day? I'll be glad to. In fact, I'll show it to you next lecture. I'll pick it up and show you. It's a fun thing. Is the sun's magnetic activity more dependent on convection or differential rotation? Differential rotation, definitely. It's that differential rotation which is so large, and it just twists that magnetic field up. Could you give us a download link to the eclipse photo? Yeah, I'd be glad to. Let me make a point of that. Send eclipse photo. Yeah, I spent a lot of time on that. Thanks. Okay, a volcanic activity. Thanks so much. I wanted a test wallpaper for years. I appreciate that. In class one day, we should watch E.T. We should actually watch things that are more scientifically accurate, such as 2001: A Space Odyssey, such as Interstellar, or such as the TV show Expanse, although that would be a lot of time. The Martian. Yeah, The Martian's pretty accurate, other than the fundamental premise. Yeah, The Expanse is great. We actually have a few more minutes. Any other questions? And remember, to get full credit for class participation, you have to show up in chat for at least 5 lectures. Is there a way to find wormholes? We don't know. People are actually looking for that. And the question is, does a wormhole connect black holes, or is the end of a black hole wormhole a white hole where radiation streams out? And what would be the signature of a wormhole compared to a black hole? These are questions we don't know the answer to, because we don't even know if wormholes exist. And so there's a lot of speculation of what a real wormhole would look like. And a lot of the speculation has to do with the fact that in today's universe, we don't think they can exist, because it would require either multiple dimensions that we don't think exist, or negative energy, again, which we don't think exist. Is 2001 your favorite space movie? 2001 is my favorite movie of all time, and in fact, it is the best movie ever made in the history of civilization. And I've attended multiple celebrations for that movie. In 1997, we had a birthday party for Hal in Urbana, Illinois, where Hal was born. And in 2007, we had a 70 millimeter showing of 2001 at a film festival I co-sponsor in Urbana, Illinois. And we had Dave came to both of those, actually. And I was able to talk with Arthur Clarke at the first celebration. And we also had Stanley Kubrick's brother show up and talk to us, actually his brother-in-law. Would people in the ISS be able to see a solar flare happening before we pick it up? No. Again, there's the visible light of the solar flare, which you can see and comes to us at the speed of light in 8 minutes. But that's not what gets you. What gets you are the particles themselves, which are invisible. The only way you can detect those particles is when they hit your sensors. And so we have to have a satellite that is literally in space closer to the sun than the Earth is to give us that kind of warning. And there's only 2 satellites that do that. One's called ACE, and the other one, the name of it escapes me. It used to be called GORSAT. If the sun were to move slightly out of orbit, would the Earth be affected? Would we actually freeze immediately, burn up, even if the sun changed by a single degree? Absolutely. But there's, you can make that statement, but remember, the Earth, the sun is 1,000,000 times more massive than the Earth. And we cannot conceive of any technology that can move the Earth by even a nanometer. So the technology or the effect that could change the position of the sun by even the slightest amount is beyond comprehension. So it's not something. What are things holding us back from making a nuclear fusion reactor for energy? Oh gosh, the problem is that you require about 10 million degrees. Actually, with the sort of reactions they're talking about 100 million to 1,000,000,000 degrees. How do you contain 10 million degrees? You cannot contain it with a bottle, because anything made of matter will instantly melt and will disintegrate into plasma. So the only way to contain that reaction is with magnetic fields. And the problem is magnetic fields become unstable very quickly, as you saw in the lecture, where the magnetic field of the sun becomes unstable very quickly. And for the last 50 years, we've been trying to figure out how to stabilize that magnetic field to contain the fusion reaction. Now, we've made fusion reactions, but they only last nanoseconds before the magnetic field is blown apart. So Europe is spending hundreds of billions of dollars. The United States has pretty much bailed on the project, building what's called ITER. They've been working on it for 10 years. They're going to be working on it for another 20 more to make a super massive tokamak fusion reactor that they think will actually be the breakthrough. But there's other smaller projects around the world to try and make other fusion reactors. And it's really that stability issue that's the big one. There's a bunch of other minor issues. The best fusion reactor, we think, should be fueled by, not by hydrogen, but by what's known as helium-3. The only place you can find helium-3 in bulk is on the surface of the moon. And so if it turns out that the only practical fusion reactors that exist are those that are helium-3 powered, then we were going to have to mine the moon for that helium-3, which is kind of interesting. If we colonize Mars, would people who live there have any protection against solar flares? No. In fact, that is one of the major reasons that Mars is going to be so challenging. So I heard once that the solar wind was the reason Mars has no atmosphere. Is that true? That is absolutely true. Mars does not have a magnetic field, and so that solar wind, instead of being deflected, hits the atmosphere straight on and strips the atmosphere off the surface of Mars. So the lack of magnetic field on Mars is a big, big, big deal. Not only does it strip the atmosphere, but it means that if you're on the surface of Mars, your radiation load just routinely is very high, and you are unprotected from solar storms. And if we have any sort of colonies on Mars, they're going to have to be underground, a deep underground, like 20 feet underground. So Mars is much, 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 much more difficult than anybody understands. And that even if you had miraculously some science fiction technology to recreate the atmosphere of Mars, the solar wind would strip it again. So the Earth already moves closer and farther away from the sun since it's elliptical. Yes, that's true, but it's just ever so slightly elliptical. It's so circular compared to other orbits that it looks to the eye as completely circular. And this is contrasted with Mars, which has a fairly elliptical orbit, and Mars gets quite a bit closer and farther away from the sun than the Earth. We could all just jump on one side of the Earth at the same time and move it. No, you can't. If you've taken physics, you can explain why that is. There's something called conservational momentum. You used to have a debate with Elon Musk right in your corner. Elon Musk is an incredible entrepreneur. He's a great engineer. He's a piss poor scientist. Sorry. He strikes me as very much like Edison. Edison was also a great engineer, but a horrible scientist. I mean, the way that he made the light bulb was he just tried thousands of things. And our world is made by great scientists and great engineers. We need both. And we're out of time. I will post that image of the eclipse. I will post this videos, and I will see you next on Tuesday. This has been fun. I hope this has been an uplifting lecture. Bye-bye.
Thank you.
Thank you.
Good one.
You too.
Have a good day, Brian.
Thanks. I appreciate it. You too. I get to go flying tomorrow if the weather holds.